Good afternoon, everyone, and welcome to the second colloquium talk of this year. Today we have Dr. Srashti Dwivedi with us. Good afternoon, ma'am. Dr. Srashti Dwivedi has a doctorate from IIT Delhi. She has done Masters in Mathematics and Bachelors of Science, Mathematics Honors from University of Delhi. Her area of research in her doctorate was combinatorics, specifically Ramsey theory. Dr. Dwivedi has research interest in areas that explore additive number theory, graph theory, and other aspects of Ramsey theory, or in general, combinatorics. She has published papers and presented in renowned national and international conferences. She has been an active volunteer with bodies and events such as Mathematics Olympiad and SPIC-MACAVE. We are pleased to have you, ma'am.
Thank
Welcome
you.
to St. Joseph's University. Can we all give her a big round of applause?
Thank you. So, should I start with this thing? So, I'm very old school, whether it is in a classroom or giving a presentation. So, I'll keep it conversational, but at the same time, it would help if at least one of you stays awake through the entire presentation. Okay, I'm not expecting everyone, just one of you should stay awake and I'll stay awake. Others can sleep, that happens in the classes also. So I'm very used to it. There is no harm done. I did the same. Kids in my college are doing the same. You also feel free to do the same. Okay, because this is going to be awfully boring once it starts. Okay, so my name is there, the area is there. Let's move. This was something that was put in flyers, the first para that is there. Okay. Now that's a very fancy way of explaining what is an Ramsey theory. And I'll reiterate the entire idea. The idea is what? I give you an infinite set. And I'm starting with that infinite set and I'm saying that that particular set has a certain property. Now what you're doing is that infinite set, you are partitioning into some finitely many classes. So you're starting with the infinite set. I'll go to the board. For now, you just listen. You're starting with the infinite set and that infinite set has a certain property. Now what you're doing is you're partitioning that infinite set into finitely many classes. What you want to know is, will there be at least one subset or will there be at least one class which will retain the original property? Okay, that is a crude way of saying things. That is what you're doing in Ramsey theory. Now that property, structure, this is something that we look upon. Now, we should thank this guy for actually starting with this area. Frank P. Ramsey, he died at the age of 27 and rightly so. If somebody is working in that area, you can also think that by 45 I will be dead. Okay, there's one area where you pull your hair out because it's like, it's frustrating at times, but the thrill when you get to the answer or when you prove that this is not the answer, even that is a certain high. Even that is a certain high, but the time period before that is certainly like, okay, next day I should be dead if I'm not getting the result. Okay, so he died at the age of 27, but he was actually trying to do what? He was trying to prove Fermat's last theorem. Now, Fermat's last theorem, I mean, I don't have to tell you what is Fermat's last theorem, but it is a certain algebraic expression, and he was trying to prove that expression. People have been trying to prove that expression so long, so forth. He also tried to do the same. He wasn't able to prove it, but what he could prove in there led to the start of Ramsey theory. Now, this is a better way of saying that introduction, that there is an infinite set, it has a certain property, and you are partitioning the infinite set. When you say that you're partitioning the infinite set into finitely many classes, the moment you go to the literal working thing, then those finitely many classes will be denoted by colors. So if you are saying that your infinite set is partitioned into some p classes, then I can frame the same thing saying what? I'm partitioning the set with p colors, or I'm coloring using what? P colors to partition the set. Because the moment I move to the next slide, I'll start saying what? Instead of classes, I'll start saying what? Colors. Okay. So I'll switch to colors because that is the easier way of putting the things. And I think so the last one you can read, it's an intersection. I see my area as what? It's an intersection of combinatorics and number theory. But people have actually extended the work to topology and geometry and all those things. People do that. So how they do it, that is still something that even I have to figure out. How many of you know the pigeonhole principle? Can anyone explain it to me? It's already written there to a certain. That way even I'll know that you are awake. What's a pigeonhole principle?
N holes.
Hmm.
Be one pigeon. So there will be one such hole where there will be at least two pigeons.
Isn't it? So now I started with what? I have an infinite set. It has a certain property. Now I'm moving to a very smaller version of it, pigeonhole principle. There I'm having what? Finitely many n holes, isn't it? And I'm saying what is the property? Not exactly the property. The conditions that I'm imposing are what? Every pigeonhole should have at least what? One pigeon. Now, once you start following that condition, you know that every pigeonhole needs to be occupied by one pigeon. But the way pigeons are, there will be at least one pigeonhole that will be having two this thing. Now, there were some pre-existing conditions. You had certain criteria and then you get to the answer. I would say Ramsey theory is a broader refinement of pigeonhole principle. Okay, because when I was doing my coursework and the very first class, we were starting with what? Pigeonhole principle. Then from pigeonhole principle, you move to something else, and then you move to finally to the Ramsey theorem. So it's like you have pre-existing conditions, you have a certain criteria. Now you want to a further refinement. Okay, so it helps that you know the pigeonhole principle. I typically worked over the set of integers. So I was saying what? I have an infinite set and I'm partitioning it into some classes. For me, that infinite set was what? Set of integers. But theoretically speaking, that infinite set could be anything. Okay. My area had what? The infinite set as integers, but it could be anything. So that's the main theorem. I'll give you some time just to read the first one and then I'll start explaining. Since there are slides, you should read also something. So what do you crudely understand just by the things there? You're starting with what? There are few things that are given to you. R, K and L. So I was saying what? You have an infinite set and you're partitioning it into classes. Now the number of classes for me is what? R. The number of classes for me would be R. And I'll be saying what? Instead of classes, I'll be saying what? R colors I'll be using. K is the final thing which I won't look at, and I'm looking at myself, not the PPT. Yeah, sir. Thank you. So K is something that we'll figure out. L is also something that we'll figure out. So you have what? You are using R colors and you're working over a set. Now, in Ramsey theory, or when you are solving problems in Ramsey theory, what you are looking for is, given these conditions, you want to look for a number n. You want to look for a number n. Now, if I go with the classical definition, I would say what? I give you a set, it has n elements. This is the number that I'm looking for, and I'm working with a set which has n elements. And what you're doing is, you are taking all possible k subsets. That means what? Every subset of size k is under consideration. And every subset of size k is colored using your R colors. Every subset of size k is colored using your R colors. Now, you are saying what? Give me a set which will be further contained in what? That set is again coming from this n element set only. The size of the set would be what? L. The L that is written here, such that what? If you are looking for every k subset in this set of size L, every k subset would be of the same color. Okay? Too many things in one go. So you have R, you have K, you have L. And I'm looking for the number N. I'm looking for the number N. For me, since I'm working with the classical definition, I would say what? I'm looking for a set of size N. Now this value of N will depend upon R also, K also, and L also. Now R is the number of colors, or R is the number of classes that you will be partitioning the set into. Okay. But when I say that you are partitioning your set into R classes, I'm not randomly partitioning everything. What I'm doing is, since I'm working with a set, from this set of size N, I'm choosing every possible subset of size K. How many of you are okay in combinatorics? So let me ask you this thing. I give you a set of size 3. So you have A, B, and C there. And I ask you, construct all possible 2-element sets from this set. 3C2. So you have a count that I will have 3C2 sets of size 2. And you can actually give me those three sets also. There is AB, there is BC, there is AC. Anything else? Nothing, isn't it? So now, instead of going to N, R, K, and L, if I'm working on this set, I'm saying what? You have been given this set, and so for example, I was taking what? I was starting with the set ABC. So I'm starting with the ABC set, and I'm picking out every subset of size 2. And I'm coloring that subset of size 2 with 2 colors. So when I move to the set, either I can color it with red color or green color. Similarly, this set I can color it with red color or green color. Similarly, this set I can color it with red color and green color. And so, since everything has 2 choices, how many total choices are, like how many total colorings I'll have? Two raised to the power 3, because I have 2 choices here, 2 choices here, 2 choices here. So you construct all those things. Now, L is something that is coming from N. So my problem is, I have to look for N such that in case if I'm taking R as this, K as this, let's say I also define for you, L should be 2, then give me N value such that from this set of size N, I can have a subset of size 2 such that if I color every subset of size 2, it will be monochromatic. By the way, what is the meaning of the word monochromatic? Same color. Okay. And color and classes I'll be using what? Interchangeably. Okay. I'm pretty sure even now it will be vague, but that is like the starting point. You are still better. It took me years just to get the definition across. to somebody who was asking me what is the definition. Okay, so this is the generic definition. You are starting with the set and all those things, but people try to do what? You are working with the set and all those things, that becomes very vague. So people try to do like modify this problem in a simpler way. One modification is what? Graph. One modification is what? Graph. Because when you visualize things, it becomes a lot more easier. If I tell you there is a set of size n and k is something, l is something, and all those things, you can listen to it, you can think about it, somewhat in a vague manner. But if you can't visualize it, it becomes difficult for you to get to the final thing. So in Ramsey theory, there are like 6 major theorems. Now, out of those 6 major theorems, 3 of them are over the set of integers. One is over any random infinite set, and there are other 2 also. Okay, there is a n-dimensional space and there is a finite field. So I worked over the set of integers. So this is the graphical definition of the Ramsey number. I would again tell you to read it and then we'll get to it. So is everyone done with this part? If you go there, I was saying what? I'm looking for that small n and I have been given what? R, K and L, isn't it? And taking all those 3 things, I know that the value of n will be depending upon all the 3 things. Now, since I find that definition very vague, I move to the graphical sense. In graphical sense, what they're saying is what? Instead of giving you R, K and L, I'll give you M and N. So M and N values that are given to you as an input, taking those things as an input, again you are looking for, instead of small n, I'm looking for what? Capital N. Such that what will happen? If you are looking for this capital N, with this capital N, you will draw a complete graph. Kn, you know what's a complete graph? Every possible edge that is there in the graph, you draw it. Okay. So I am saying what? You look for the number capital N and it should be the smallest n. Okay, I'll tell you about what is the meaning of the smallest n. So you're looking for n such that if you draw your complete graph Kn, then either, now one more thing that you should read there it was what? R, K and L. Now there I have given you how many inputs? 3. Here I have given you 2. Because by default they assume what? If I have given you M, N, then what is the count? 2. So I am dividing that graph into 2 parts or 2 categorization or 2 classes. Okay. So now what they're saying is, since I have 2 classes, let me call the first class as red color, second class as blue color. Okay. So what they're saying is, if you are working with Kn graph and you draw every possible edge, okay, now every edge that is there in the graph, either you can color it red or blue. And this way you will have exponential number of colorings, isn't it? You will have all those colorings. Now, if you are saying capital N is the Ramsey number, then what it means is every possible coloring that you have of this graph will either give you a red Km or a blue Kn. That is your Ramsey number. Okay. So I hope this is somewhat clearer. Okay. Classes needs to be given and there is a certain input that needs to be given. Okay. And whatever set that you are considering, it will be up to you. Whether you are working over the set of integers or numbers or anything else. Okay. That will be your choice. That's why you say that in Ramsey theory, you have many classifications. Whichever one you find it as a starting point easier to work with, pick that and then move forward. Okay. So I'll move to the, if anyone is taking graph theory and all those things, I think so this is something that comes, the party problem, R33. So anyone can explain this problem to me? recently I had to revise the syllabus, so I saw that it's there in every this thing R33. So that's a Ramsey problem. So if you can explain that to me, it will make things a lot more easier. So the problem that is there, and so for you, what is red, what is blue? Exactly. So classes is a broader thing. Colors is something that I'm using because I don't want to talk about the classes. So I'm saying what? What you are saying? Red is what? They are friends. And this means what? They are not friends. Isn't it? So that becomes the classification. And if you pick any two people, either they are friends or they are not friends. Isn't it? And since your Ramsey number is what? It works on a complete graph. So if you, first of all, I'm claiming what? The Ramsey number in this case is what? 6. Isn't it? In this case, it is what? 6. So if you are drawing a K6, and for every possible coloring of a K6 graph, either you will land up with what? Either a red K3 or a blue K3. That means what? 3 of them either know them, they are friends or they are not friends. And how many colorings are there? How many edges are there in K6? K6? And then, so it's a 30. So let me call, I have a string of length 30. How many colorings are there? 2 raised to the power 30. So now at this point of time, the idea wasn't to tell you that R33 is 6. Okay. The idea was what? Problem is, I have 6 people there. But what I am partitioning is not 6 people per se, but it is the relation between those 6 people. Now those relations are denoted by some 30 edges. Those relations are denoted by 30 edges. And every edge can be colored with 2 colors. So I said what? You start with 6, you move to 30, and so I draw a string of length 30. Every entry can be given 2 options. So you land up again with what? 2 raised to the power 30. So the difficult part of Ramsey theory is what? If you are proving that 6 is the Ramsey number in this case, then you have to prove that for every coloring, and you have to consider how many colorings? 2 raised to the power 30 coloring. For every possible coloring, you are either landing up with a red K3 or a blue K3. And that's why, if you'll actually Google it, there are very few Ramsey numbers that are known. And the problem becomes harder the moment you move from 2 to 3 colors. So even with 2 colors, there aren't many results. There aren't many results with 2 colors. And that's why the moment you go to 3, nothing. There is a generic theorem, Ramsey theorem with n colors, but that's it. For like 100 years, there's only been one theorem with n colors. People, there are some like proofs, they are proving upper bounds and lower bounds. But the thing is, complexity is too much because it's what? It's an exponential problem. So that's why it becomes harder proving something in Ramsey theory. Proving something in Ramsey theory is harder. Even proving that something is not there is also hard. Okay. So that is the other thing. How many of you have actually proved this thing when you like, is this thing there in your syllabus? It's there in your syllabus. So I actually proved it. So how did you prove it? Good. And so this is my work. Okay. This is what I did. I mean, a very minute part of it, but this is what I was working on. I wasn't even working with graphs. I was working with what? integers. So I'm saying what? Give me an equation. I can pick a homogeneous equation. I can pick a non-homogeneous equation. Okay. And by the way, what is the difference between the two? It's equal to 0. The other one is equal to some non-zero, this thing. So I'm saying what? Give me an equation. And what I'll do is, I will color the set of integers. I'll color the set of integers. And once I color the set of integers, I should land up with a monochromatic solution to the equation. Okay, I should land up with a monochromatic solution to the equation. So if you want to read it, you can read it. But reading it will give you a vague idea. We'll move to this thing. So far, anyone has any doubt? Obviously, you have many, but we have 1 hour. So the vaguest doubt that you have, you can ask. And I'll answer as vaguely as possible. Any doubts that you have? See, that's the best strategy. Somebody asks you a question, you are not able to answer it. Give them such an answer that, they're like, okay, I might not be able to understand it. There are many cases. There are many cases when it won't exist. In graph Ramsey theory, I can't tell you, but when I was doing my PhD, I picked up a certain equation, and in 1.5 years, I only proved that the number doesn't exist. And that is not a research paper. So one thing that you should know, it is not necessary that every time it will exist, this Ramsey number. Obviously, the theorem says what? I can find such number, isn't it? But when you're finding such number, there are certain conditions that are involved. Is it? How should I give you an example? Okay. My work was what? I was given an equation and I'm coloring the set of positive integers. And I'm just telling you, give me an equation and I'll look for the Ramsey number. If you are coloring the set of positive integers and I give you an equation where the solution, no matter what, will also involve a negative integer. So I'm saying what? See, I am coloring the set of positive integers and you are giving me an equation. But if you give me an equation such that what? No matter what kind of a solution I look for that equation, it will always involve a negative integer. Then I won't have a Ramsey number because the set under consideration is what? Positive integers, isn't it? So the thing is, when you say that the Ramsey number will exist, if you remember the first slide, there are some pre-existing conditions and I'm looking for more conditions that I need to impose on this set such that the Ramsey number will exist. So in Ramsey number, when you are proving something, it boils down to what? Either you can prove that it will exist or you will land up with the answer that it won't exist. Now, both of them will take the same amount of time. Just that you can only get a research paper when it exists. You don't get a research paper when it doesn't exist. Okay. So that then goes to garbage. So these are the theorems. You're already gone and I have to speak. So on integers, these are the 3. So I talked about that in Ramsey theory, there are 6 classical theorems. 3 are on integers, 1 is on n-dimensional space, infinite set, and so on and so forth. These are the 3 theorems on integers. Now, in all the 3 theorems, you are coloring the set of positive integers. Okay, for all the 3 theorems, you are coloring the set of positive integers. Just that in van der Waals theorem, the structure that you are looking for is a arithmetic progression. In Schur's theorem, they are talking about equation. So they are looking for the equation this kind. Here you have 3 variables. The generalized has what? N variables. In Schur's theorem, they are looking for this equation and they are looking for a Ramsey number. Rados talks about a general equation. You give me some 2x plus 3y is equals to 5z, or you give me 2x plus 3y is equals to 19. I am looking for the Ramsey number. So the progression goes like this. When people have to read the book, they start with van der Waals theorem because there you have many results. Then they move to Shor's theorem, and then it is Rado, because it keeps on getting refined. Okay, the equation becomes too many, but the results become fewer. Okay, so that's how it will go. And by the way, Rado was a doctoral student of Shor's. So that's why Shor was considering the equations where the coefficients are what? Either +1 or -1. So if you write it on this side, it will be 1, 1 and -1. Rado did what? He added coefficients. And Shor's equation is what? Homogeneous. If you take your z to that side, you land up with what? 0. Rado did what? He took any set of coefficients and he took constants or 0. I don't know if I should be telling you this thing or not. By the way, how many of you actually want to do research? Oh, 1, 2, 3. You were yawning. You will be sleeping a lot in research then, PhD. Not you. Last one. When he was asking the question, just a moment after that, you were yawning. In PhD, 6 years, you will do what? What? It's okay. I slept a lot. You also sleep a lot. There's nothing else you can. Either you get the results or you sleep. So, I was telling you what? It's people always try to work with 2 classes or 2 colors, because the moment it goes to 3 colors or more, it becomes very hard. But the generic definition goes for R colors or R classes. So this slide is only about that. So you can read it, but I don't want to explain it because we won't be talking about this thing. Okay, it's there, so you read it. That way I can also, relax. I'm very good at realizing who is checking the message. You are sleeping? It's okay, it's okay. So before I move towards, like, I just want to give you the basic idea of all the things that were done. And after that, we'll move to proving, like not exact. We won't be proving anything. I'll just tell you how things are proved when somebody tries to look for a Rado number. So I actually worked on Rado numbers. We start with Ramsey, we start with infinite set, we start with graph, and then we move to integers. In integers, we have 3 theorems. Out of those 3 theorems, I worked in Rado. Okay. So when you're proving something there, how you go about proving is something that I'll talk about, not actually the proofs. Okay. This is one of the, how should I say, offshoot of Rado numbers. So if you remember the definition, I was saying what? You give me an equation and I look for the Ramsey number, isn't it? But it's not necessary that you need to work with a single equation. I can also work with a system of equations. Okay. So if I'm working with a system of equation, now system of equation can involve 2 equations or more. But if you're working with a system of equation, then I can ask you find the disjunctive Rado number. Okay. If we get the time, we'll talk about the disjunctive Rado number. But just remember this thing. If I give you a single equation, I can talk about Rado number. I give you a system of equation. One possible classification could be disjunctive Rado number. Rado number can also be calculated for a system of equation, but the results are not that many. So that's why people switch from Rado to straight away disjunctive Rado. So basically, the third point there, that is the equation that I was working with. So if anyone actually picks up my thesis, nobody will. But if somebody does, this would be there on the first page. After a lot of insults and scoldings, this was the title. Okay. Summation ai xi minus xm is equals to c. So if you remember, Shor's equation was what? X plus y is equals to z, and I can write it as x plus y minus z is equals to 0. And if you generalize it, it will be what? This thing, this is the generalized form. Now, Rado is what? You just simply add the coefficients to this equation, isn't it? You add A1, A2, A3 and so on, and you land up with the equation. So I did the same thing. I added coefficients and the last one I retained as it is. So the negative one I retained as it is, but to the remaining I added the coefficients, AIs. And instead of having 0, I had a C. So I was working with the non-homogeneous equation and I was looking that under what conditions I can find the Rado number for the given equation. Okay. So my entire research was what? I have given you some AIs. Those are the coefficients of the Xi's. The last variable will always have the coefficient as -1. You will also have a constant C. Okay. These things will be given to you. And if these things are given to you and you are always coloring the set of integers in 2 colors, that means what? You are only partitioning it into 2 classes. So if I give you AIs, if I give you C, and you know there are some M variables there in the equation, and you have 2 colors, is it always necessary that you will have a Ramsey number? If it does not exist, what are the conditions I should have on AI, C and M? If it does exist, again, what are the conditions I have on AI, M and C? That is the entire body of research. So you come up with the conditions. There is actually a theorem that says what? If AIs are in a certain way and M is a certain value and C is a certain value, then Ramsey number won't exist. But in every other case, it will exist. Wherever I could find the Ramsey number, I did. But because that becomes very hard, people go for the next best thing. See, either you give me the, so if anyone is actually interested in stats, either you give me the actual answer or you give me the approximate answer. When you're giving an approximate answer, the idea is what? You can actually say that your actual answer is within a certain range. You say what? Your actual answer is actually within a certain range. With that range will have a lower end, that range will have a upper end. So if I can't find the Ramsey number, I'll give you a range. Because giving a range also means what? I have proved that the Ramsey number will exist. I don't know the actual answer, but proving that it exists will make things easier for the person who comes next. Okay, you know that the answer lies between this and this. Now you do something with the coefficients and all those things so that either you shorten the range or you give me the exact answer. So when you're proving something in Rado, either give me when it does not exist, otherwise give me when it will exist. If you can, give me the actual value. If you can't, give me a range. Okay, that is how people prove things in Rado. Disjunctive one you don't read because I don't know how much we'll be able to cover it. My writing is very bad, so I'm saying what? I have given you I'm finding a Rado number. Let's say I'm claiming N is a Rado number. I'm not even going how we are proving something, but let's say I'm saying what? N is a Rado number. I'm always using what? 2 colors. So I have how many colorings to consider? 2 raised to the power N. Now, see, when you are trying to prove something, obviously you will use your coding and all those things. Now, if you are using, I'm talking about the proving techniques or the aid that you can use in order to prove something as a answer. So if you are doing the coding part, you are claiming N is the answer, but in order to prove that N is the answer, I have to check how many colorings. 2 raised to the power N coloring. And every coloring should give you the monochromatic solution of the given equation. That means what? X1, X2, Xn plus 1. Everything should be of the same color. Either all the Xi should be red color or all the Xi should be blue color. So if you have 2 raised to the power N colorings and let's say you You code your problem. So that means what? You write a code where you are given an equation ax 7x plus 5y is equals to 19. Now the way you will do the coding is, first you find out the solutions. If that is the way you want to code, what we do is, if I'm conjecturing, let's say I give you equation what? 2x plus 3y is equals to 5. And let's say by some hit and try, I'm not telling you how, but some hit and try, I am claiming that 17 is the answer. For this equation, 17 is the Rado number. So you have 2 raised to the power 17 colorings to check. The way you will write the code will be what? Your code will generate all binary strings of length what? 17. Is this part okay? Your code will generate all binary strings. What is the advantage of binary strings? Or why binary strings? Why not a tertiary string, or why binary strings? 2 colors, isn't it? Because I'm considering 2 colors. So I'm considering all possible binary strings of length 17, and every string that I have gives you a certain coloring, and now you start looking for a solution. So when you run that code, the problem is, since it has to check for a solution 2 raised to the power n times, unless I give you very small values of AIs or M and C, unless I give you very small values of AIs, M and C, your code won't run. So in the second year of my research, because you don't have too much existing theory, the research area is what, 100 years old, you don't have too much theory to work on. So the first target is always what? Write a code, get the answer. Now when you go there, they'll tell you what? Since your problem is exponentially times hard, unless you filter out lot many scenarios, the scenarios where there is a straight up answer, your code won't give you anything, because it will become a lot slower. There is a big O notation. Big O notation tells you what? The time complexity. For how long a certain code will run. If it is 2 raised to the power n time, that means what? It will become very slow. It will become very slow. So coding will only help you if you take very small values of A, M and C. So the first target whenever you are trying to look for the Rado number is, since your coding won't help, take very small values of A, C and M. For very small values of A, C and M, your code might generate certain answers. Okay. If your code is generating certain answers, then from those answers, try to guess your Rado number. Okay. So I told you what? That I'll tell you how you go about proving things in Rado. This is the first thing. See, you want in Rado or in Ramsey, there is no this thing that you can only use topology, real analysis or something. Every branch of mathematics is open. If you want to prove something is a Rado number, you can use every branch of mathematics in proving Rado number or Ramsey number. Because it's when you put things on a board or paper, it's very big. So it's open to everyone. But you have to come up with some initial tools so that you can conjecture a certain answer. Okay. So coding will help you only if you give some very small values of A, C and M. Okay. How many of you are still awake? And by the way, what is the time? Okay, that's it. So, should I tell you a bit more or you have some questions? As in, so there is a person, T. Gabels, he has actually proved that if it exists, there is a certain upper bound. Your Ramsey number won't go beyond this thing. Even I haven't seen the result, but yes, he has proved recently. That's like a big thing. Knowing that, it won't go to infinity, no matter how bad a upper bound is, it puts a cap. That if I'm going to run a code, I know that this is the upper limit. Again, the code won't run, but knowing that gives you a certain sense of relief. Okay, and if you start putting a cap, so see, I'm not saying coding won't help. It certainly helped me in many cases. It helped me in many cases, but the thing is, you have to realize how to use the code. When we were told no, that it won't help you, then we refined it what way? This is the general equation. Let's go for simpler values. So if I'm considering ax plus by is equals to c, I will do what? I will take a only as 1 and 2. I will take b only as 1, 2, 3. I will take c only as 1, 2, 3, 4. That means what? For a, there are only 2 possibilities. For b, 3 possibilities. C only 4 possibilities. Take very small values and you would like to think that it might land up with a certain answer. Okay. So when we ran the code, we got some 7 values. And then the idea is what? Fitting of a curve. Anyone remembers? Numerical methods. So if you get a certain answer, you try to fit in an algebraic expression to that answer. So if I get certain, how should I put it? So let's say you're getting, so if you, let's say I got the answer as 1, 4, 9, 16. 1, 4, 9, 16. Then what would be the generic idea? N square, isn't it? That kind of a thing I did. I got a certain answers. I tried to put in a algebraic expression there, and that was the starting point. If for these values n square is turning out to be the answer, maybe for every case n square is going to be the answer. So that is how you start proving things. And certainly having upper bounds is a major plus. Okay. Any other doubt? Stay awake only for 15 minutes. Okay. Thank you. Somebody said yes. Now, so I was saying what? You're proving Rado number and how can you use your coding part. Let's say somebody understood something in that. Now, when you are putting those things on paper, you conjectured some answer. For me, that answer is n square. Okay, let's say you are saying what? N square is the answer. Now, in order to say that n square is the answer, you should have actually a mathematical proof, isn't it? That is your entire idea of research. You should have a mathematical proof. Now, here I'll come to your least this thing. So, I'll go back to your R33 is 6. When you are saying R33 is 6, that means what? For every K6, you are considering your K6, every coloring of K6 is either giving you a red this thing or a blue this thing. Now, what about the number 5? R33 is 6. That means what? Every coloring of K6 is either giving you a red K3 or a blue K3. What about 5? Why 5 is not R33? That's what I'm asking. 6 is R33 because certain thing is happening. Why 5 is not R33? I'll give it a pass because you are awake. Other thing? My problem is what? I'm conjecturing n square is the answer. Now I have to prove this thing mathematically on paper n square is the answer. Ramsey number is what? It is the minimum value n such that what? No matter how I color it, either I'll have something in red color or I'll have something in blue color. Now if I have to prove it on paper, for n square I'll say what? No matter how you color this set 1, 2, 3 to n square, the property is there. What about n square minus 1? That's why I'm putting it here. If you are claiming R33 is 6, that means what? For every edge coloring of K6, you either land up with red K3 or a blue K3. And that is why this is the graph Ramsey number. Why 5 is not a graph Ramsey number is what I'm asking. The better way to put would be what? K6 is a 6 is a graph Ramsey number, okay. 5 is not. Why? Because if you draw your K5 and I can get even one edge coloring of K5 such that what? Neither I land up with a red K3 nor I land up with a blue K3. Then my condition is not met. R33 says what? R33 says what? If you are edge coloring a graph, then either you should land up with a 3, K3 in red color or K3 in a blue color. And 6 is satisfying that property. No matter how you edge color the graph, it will give you either red K3 or a blue K3. This one says what? I can give you at least one coloring of K5 where neither you will have a red K3 nor you will have a blue K3. Similar kind of thing that you will do it here. If you are saying n is a Radu number, I will say for every 2 raised to the power n colorings, I will have a monochromatic solution to the equation. And since n is the answer, that means what? N minus 1 is not the answer. If capital N is the answer, n minus 1 is not the answer. That means what? Out of the 2 raised to the power n minus 1 colorings, I have at least one coloring where I won't have a monochromatic solution. Okay. So, whenever you are trying to prove something, you will prove your things in two parts. One part where you consider 2 raised to the power n coloring. The other part is what? Where you are proving n minus 1 is not the answer. And that is why n is what? Least value. If n minus 1 is not the answer, n minus 2 is not the answer. If n minus 2 is not the answer, n minus 3 is not the answer. So that means what? 1 is not the answer, 2 is not the answer, 3 is not the answer. Till n minus 1, nothing is the answer. Because for every value, I can find a coloring where the criteria is not met. N is the first number where the criteria is met. And if n is the smallest number, see, if n meets the criteria, then you add one more thing. It will meet the criteria. Add one more. It will meet the criteria. That is why n is the smallest. Okay. So that is why proof is done into two parts. Okay. Should I continue or do you have questions? I mean, I don't think so. I'll tell you about the proving techniques. But read about the greedy algorithm. That is like the most basic way of proving one part of the things. I think so. I'll stop there. Anyone has any doubts? No? That's it. Let me take this. Don't worry, at least you asked two questions. I'm thankful for that. You asked two questions. Normally, we have to give the chit to kids that ask those questions. I got to realize this thing recently that we were told that there is a seminar. Tell kids to ask questions. So you can ask this question, that question. So you ask questions. So I'm thankful for that. Yes. So I was Googling this thing, SAT solvers and all those things. I don't know how, but see, even otherwise, the way I see it, there are, I was using colors, but classification is done in every, this thing, huh? I give you any modulo M. Modulo M is what? You have a set of integers, but I don't want to work with the entire set of integers. If I reduce it to modulo M, I only have to work with what? 0, 1, 2 till M minus 1. The modulo classes, I can see it also in colors. Modulo is also done in context of what? Algebraic and algebraic relations. Isn't it? So that way I can see. People have written a lot many things that how can be applied. I don't understand it either. But yes, I see it in context of modulo. That is the best way I see. That is the best way to understand why you don't want to work with the infinite. Nobody wants to work with the infinite. The idea of refining things is this only. Working with the infinite set means what? You are wasting a lot of energy, time, and you are definitely not landing up with the answer. Partition it into classes, maybe you can. That is what we are doing here. And we are doing it for an equation. Okay.
there are no more questions. It's time to speak. Thank you, ma'am. Let me just take your words. Like most of you, many of them are doing the final year PG project in draft theory. Yeah, I mean, imagine group of people. So mostly you'll be probing something like, suppose let's say inverse domination. Many of you are doing inverse domination or a graph perfect dominator coloring number. Okay, and you'll be saying that for this graph, this is n. Yeah, maybe or n square or some bound you'll be finding, right? So what ma'am said is really important. If you're saying the answer is n, you should be saying that it doesn't exist for n minus 1 or a lower bound. So many papers miss that. Okay. So if like they will say the answer is equal to n. Your proof is valid if there are two parts as ma'am told. Like the answer exists in n and the answer doesn't exist in minus. So I'm not teaching you guys, I mean, second MSc I'm not teaching, so I will not get them as a group to say this. But when you're proving, yes, your results now you're taking a baby steps to find the answer, right? They're still not reached, isn't it? Or you already got the answers. Some of you have got the answers. So when you go into the proof, the two parts are important. That is how it exists and why it doesn't exist for the load. Thank you, ma'am. I think you guys can. I think their classes got over at 12. Their classes got over at 12:50, right? And the first time we had a class, we rescheduled. Thank you for staying by. All about steps. Thank you, God. I can just put a message that comes from the lunch. Yeah.